Hi everyone, welcome to this session on RFI Gaming and Entertainment. I am Nikunj Raghuvanshi, the research lead for this area. To start the session, I'm pleased to welcome CJ Williams today, who is the entertainment lead in Azure Industries. Hey CJ, it's great to have you with us today.
Hey, it's great to be here and talk about entertainment with you.
Yeah, so could you tell us a little bit about Microsoft's focus on cloud tech for the entertainment industry?
Yeah, absolutely. When we think about entertainment and the cloud, it really starts with the creator, right? There's lots of types of creators, professionals, large companies, people who are just doing it for a hobby, and they all have one goal in mind, which is to entertain their fans. And what we're looking at or what we're focused on is really being able to empower those creators, whether they be game developers or someone who's doing a video or music, empower them to basically realize their dreams of entertaining their fans. And so that's our big focus. And we're looking at it across the board from where they're actually creating and how we can bring things like AI to help them create the best experiences they can, all the way to how they actually engage their audiences and how they can understand what their audiences want to be entertained with. And so our focus is really across the board to empower them to, as I said, realize their dreams and entertain their fans and entertain those that are looking at what they're doing.
That sounds super exciting, CJ, and thanks for joining us today.
Yep, great to be here.
Several ongoing technology trends inform our research at Microsoft. I'll note a few here. The tools for creating digital content in movies, TVs, and games are converging. For instance, game engines are moving towards photorealistic rendering techniques that have been used in movies, and movies are trending towards virtual production using game engines. So one can imagine a future where massive virtual worlds are created directly in the cloud with a common set of collaborative tools. For distribution, cloud streaming is already standard for movies and TV, and a similar trend is occurring with game streaming, such as Project xCloud. Pixel streaming with game engines allows creators to deploy 3D applications to the cloud, which users can then interact with in a web browser. And lastly, media consumers are no longer passive. This is already true with esports and streaming, where communities are built around games, but is now accelerating towards games acting as cloud hosted social platforms. For instance, Minecraft, Fortnite, and Roblox, where users socialize, create, and exchange artifacts and experiences, which brings a lot of value to these platforms. At Microsoft Research, we have a diversity of projects addressing the hard problems for this future. Let me highlight a few. Project Acoustics brings automatic and detailed physical audio effects for games using the cloud to reduce months of computation to minutes. It ships today in major game franchises, reaching more than 100 million players. Game AI today is largely based on hard-coded rules, leading to non-player characters with simplistic behaviors. Project Peria at MSR Cambridge aims for a much richer game AI that learns from experience like people do. So training is vastly accelerated by parallelizing in the cloud. 3D scenes for games and movies are expensive and time consuming to create, as Kate will also talk to today. At MSR Asia, there is an ongoing research theme of deep learning for automated scene acquisition and generation, like this example rooms generated, shown here. On the consumption side, Watch4 is a cloud-powered live video analytics platform with many diverse applications. For instance, it can automatically surface exciting moments in an esports live stream, and Watch4 is currently serving 400 million minutes of video content per month as part of MSN Esports Hub and Bing Livestream Search. Then there's TrueScale from MSR Cambridge that is used by Xbox Live and many major games today. The system is used for high quality ranking and matchmaking in multiplayer games, which is crucial for player engagement. So they match with people with similar skills. Cloud hosted video content is out of reach for communities worldwide with low or no network connectivity. And Project Mishtu from MSR India is solving this problem with a novel networking infrastructure which is being developed in active collaboration with media and satellite partners in India. Finally, the lag between player inputs and game response in a cloud game setting is a major problem. So Project Galena at MSR Montreal aims to improve upon this by using imitation learning. So as you can see, we have a large range of efforts attacking core research problems at MSR. And with the RFI gaming and entertainment effort, our focus is on partnering with the industry at large to build technology to empower creators everywhere, as CJ said earlier. So, next up, I'm excited to host two technical leaders in gaming for their talks today. Aaron McLeran will talk first. He's the audio engine lead at Epic Games, and he will talk about the latest innovations in audio content creation with Unreal Engine 5 and Metasounds. And we will conclude this session with a talk from Kate Rayner, Studio Technical Director at the Coalition, who will talk about the many content creation challenges faced by game studios today. And with that, it's goodbye from me, and let's hear from Aaron. Thank you, everybody.
Hello, my name is Aaron McLeran. I'm the audio engine lead at Epic Games, and I'll be presenting today procedural game audio with Metasounds. Before I get into that, I wanted to talk a little bit about what real-time procedural audio actually is. Procedural audio is fundamentally audio that's dynamic, data-driven from many different data sources, either gameplay, input from players. It could be, game save data, etc. From any source. Fundamentally interactable. If it's procedural, it needs to be in games, often something that can be changed or varied depending on gameplay, and generated algorithmically in real time. In most ways, in fact, it's analogous to procedural graphics, which is something that games are quite used to. Procedural graphics would be graphics which are rendered in real time. And they're fundamentally required for games. So procedural audio is currently and has been required for games for a long time. Very much so in XR, and increasingly outside of traditional media or game media like music and film, especially in the context of linear real-time or virtual production, which is increasingly sort of a growing industry. And we talk about procedural versus static audio in the context here, where procedural audio, again, is algorithmically generated and fundamentally interactive, versus static audio, which would be generated ahead of time and rendered ahead of time and then sort of just played back. That would be like your media player, like an MP3 player. And some elements of both of these are typically in play in games. In cinema, it's almost always just static audio. So one of the fundamental problems to procedural content creation across the board, not just for audio, but also for graphics and any other kind of media in which the art is being generated algorithmically, is that it requires highly technical artists, systems-based thinking, and a whole new set of tools that avoid various technical bottlenecks like performance and other kinds of problems when it comes to real-time generation of content. This sort of extra cost results in a sort of higher upfront investment in terms of time and technology and sort of production overhead, but it has a huge potential down the line, once that system is created, to create massive amounts of variability and interactive content. And of course, in this sort of technical landscape, it requires tooling that supports quick iterations and previewing within an actual real-time environment, so that artists which are building these systems can preview them and play with inputs, variables, that kind of a system that allows you to actually create this content at any sort of scale. So in the domain of graphics for real-time procedural generation, there's been a number of different tools that have been developed across the sort of game industry and also in other industries. One of the big innovations that happened in the probably about 30 years ago now is the development of shaders, which is a kind of language that is standardized that allows for programming hardware pipelines procedurally very quickly, and it doesn't require a programmer to go in hard code exactly what kind of graphics configuration something needs to be in. But shaders themselves is itself a programming language, and it does require programming skills, which is a sort of high technical bar for content creators. So there's many different tools that exist out in the world that allow people who are technical but not necessarily wanting to go down to the level of programming, in text. There's tools that exist to sort of optimize that workflow to create a more easy and visual and quick environment for programming these procedural systems. So in Unreal Engine, we have, for example, the material graph, which is on the left here, and on the right is Niagara, which is a new system for programming particles. Both of these use, under the hood, basically shaders to drive hardware. And these tools allow for a significant boost of productivity at scale for generating and controlling procedural graphics. For an audio, the analogous tools really don't exist. Traditionally, tools in games are procedural, but they are basically randomly varying and slightly modifying static assets. So the typical process is that a sound designer will make a static asset in their tool outside of a game engine, import those tools, and then randomly pick from those variations and do some high-level parametric control of them. For example, volume, pitch, maybe they'll apply a filter, which is generally pretty hard-coded and programmed into a kind of pipeline. So you call it like a static pipeline for audio processing. And then panning, which also includes like spatialization, HRTF, sort of this whole domain here. So they're often in current systems is like a hard-coded sort of DSP effect pipeline. The effects themselves may be swapped out as plugins, but the general process and where the audio is processed and generated is static. And these kinds of effects might be reverb, EQ, or dynamics processing, which, sort of your standard mastering effects. And overall, the process is pretty static, and this includes all of middleware that I'm aware of and most game audio engines. There's definitely some work in this area outside of games and sort of on the periphery of games, and some middleware is going in this direction. But generally speaking, this is the traditional approach for procedural audio. And the screenshot here is sound cues, which is sort of technology in UE4, and it just basically is varying, randomly picking a variation of a static asset. So in UE5, we have some new technology we're working on called Metasounds, which is basically a new approach to audio in games. They're analogous to audio shaders in a way. They are basically a user-programmable DSP pipeline. It allows a sort of analogous tool to the Material Graph or Niagara in Unreal Engine 5 for audio. This is a screenshot here of Metasounds, and I'll give a demo real quick. So the demo I'm going to show you is inside of a project available in early access. You can just check it out, download it now today, and check out the project. This is a real Metasound used in the UE5 early access project, Valley of the Ancients, which is available for download. The Metasound combines traditional static asset variation playback and real-time procedural elements. The procedural elements allowed the Metasound to actually change its duration dynamically, either from the game or from the sound designer trying to match animations. The Metasound features a wide variety of procedural elements, synthesis, modulation, and so on, as well as traditional wave player sort of static asset playback. This Metasound I put together for a live Twitch stream where I walked through in detail how to construct this Metasound, but here I want to showcase it to talk about the sample accurate timing for the drum events. Also, the parameters are updatable live. So here I can mute the synth element here. I can also change the beats per minute dynamically. So I wanted to give a quick tour of some of the projects I've seen posted in social media with Metasounds. Check out hashtag Metasounds on Twitter and YouTube to see some of the work that people have been doing. This first one I wanted to show is from Nick Fornell here in GameSynth, where he's integrated his third-party library into Metasounds. This is a rain physical model that it can be driven from any gameplay. This next one is a project by Chris Zuko called the Project Mix. And he's integrated Metasounds into his project, and here he's showcasing the power of Metasounds with his system that he's built. So he's able to change parameters in real time. School of Video Game Audio posted this demo of a sort of procedural robot voice generator. Worm Juice Dev here is working on a procedural music system that's driving some visuals in real time. Melodic Minimal Techno here is made by Battle Angel Sound, which had a really great sounding patch here. And Arthur Barther over here is doing some cool stuff with sine tone generation and chords, driving Lumen and Nanite, which are two new graphics technologies in UE5. There are hundreds and hundreds of cool projects that people are posting. Please check them out. So Metasounds doesn't happen in a vacuum. There's a lot of precedents outside of the domain of games. There's Super Collider, Chuck, Max, Pure Data, Faust, Reactor Block, C-Sound, and Kaima, and there's probably others I've missed. In these areas, procedural audio is a huge focus, but there are sort of downsides to them which prevent them from operating at scale in games. But this is not a new idea in the context of audio. I recommend people checking these out if you're interested on the subject. So Metasounds at a high level is a directed acyclical graph. All of the Metasounds are actually rendered in parallel in background tasks using the same architecture as our decoders that we have for sounds. That means that each of the Metasounds can have independent sample rate, channel count, buffer size, and in fact they can scale as a function of time. This is one of the innovations in Metasounds that I think that separates out Metasounds from those other examples here, is that we actually have the potential to operate these procedural graphs at scale in the context of a real game. We've architected it to be fundamentally plug-inable into our existing audio rendering framework, which means all of our existing features that we have in UE Unreal Engine, like spatialization, audio propagation, submix processing, and some of those other more traditional techniques will work right out of the box with Metasounds. And we can actually have Metasounds composed within other Metasounds, which is another innovation in the context of Unreal Engine with Material Graph, etc. We can also have third parties extend Metasounds easily through a plugin node registry. And Metasounds now in UE5 actually operate with presets. So you can create a graph once and then reuse that graph over and over and over versus having a unique graph per instance. And then a really exciting feature of Metasounds is sample accurate events, which I'll talk about in more detail in a second. So real quick, this is probably too much information here, but essentially data is shared between nodes in a way that allows or prevents copying data. So for example, in here, if node A was an audio buffer output, node B, C, and D would be referencing the audio buffer in A versus making copies. And so in this way, we can optimize data flow from node to node. And it's very easy, in fact, to make new Metasounds with our API here. It's all kind of driven through modern C++. I wanted to do a little bit of an explanation of sample accurate events. Basically, we have this method where we have stored events into an array of sample indices. And so a trigger sequence in Metasounds is actually a buffer of events where each index, each element in that buffer represents an index where an event is intended to happen. And with this, we can actually subdivide an audio render callback at an arbitrary resolution. So we can actually have events happening at any point in time within a Metasound graph. So Metasounds is really exciting for us, and one of the reasons why I'm excited to present here is that I think it's an ideal environment for research into audio and perception in an interactive real-time environment. There's a lot of interesting directions that I think someone could take this technology into interesting directions. It's very easy to extend the Node API to include any third-party library tool, so machine learning systems, third-party DSP libraries, if you're doing physical modeling research, and just in general, it's a test bed to investigate new spatialization, propagation, or other perceptual studies. We're actually working with Microsoft Project Acoustics to build a deep integration with Metasounds, where we can actually get the acoustic simulation data directly into sounds and offer a really full systemic integration in a way unlike any game engine that I'm aware of has done with procedural audio with Microsoft Project Acoustics. And I think in particularly the sample accurate triggering of audio events is a new framework for investigating an interesting domain for perception. So I think timing, there's been a lot of studies that talk about latency and sort of perception on timing relative to AV sync, but I think there's a lot of interesting stuff between like sort of audio sync, what I'm dubbing AA sync, but basically event synchronization across different audio events. I think with Metasounds and sample accurate triggering, there's some interesting research in that area.
Hello, my name is Kate Rayner, she, her. I'm a studio technical director at the Coalition, one of Microsoft's Xbox game studios. I get to work with these game studios, which have some of the greatest game developers and game franchises in our industry today. Today, I'm going to talk to you about content generation at scale. I'm going to talk about how we've seen exponential growth in content through different gaming generations. A little bit about gaming virtual worlds and the metaverse, some example content challenges that we face, and I'll also talk a little bit about player engagement challenges that are open for research. What we've seen through the generations is the size of development teams grow at an exponential rate. In this graph here, you can see through the different generations of console hardware through the early 80s to 2016. On the y-axis, you see iterations of franchises, version 1, 2, 3, and the size of the spheres, the number of developers. The challenge we see coming from Generation 7, the Xbox 360 generation, to Generation 8 Xbox One, we see a typical game team size growing in 3 to 4 times in size, typically exceeding 200 developers. It's common for some of the bigger, more successful AAA franchises to have game teams of 400 to 600 developers or more. As we're moving into Generation 9, we see this trend continue. And with more limitations removed on the detail and fidelity of the content, we're able to showcase in real time. However, the cost of creating this content is spiraling out of control. AAA game teams have moved to employ armies of outsourcers and globally distributed development in order to reach scales of up to 1,000 plus for some of the most content-heavy open world games. It's as if the size of game teams have been growing at the rate of media storage and the actual content size of the games themselves. As we see in this graph over the generations, we've seen game sizes go from 4 megabytes in the cartridge days all the way up to 25, 50, and 100 gigabytes being fairly common for a late Generation 8 or early Generation 9 title. One thing that's also interesting in this graph is we see a real particular jump in the rate of I/O with the latest generation, allowing us to fill memory faster and stream even larger worlds into memory as we move around them. So who are employing these armies of content creators? Well, the reality is few game publishers are willing to grow teams to this size, except for perhaps their top 3 franchises. The costs of doing this are prohibitive, and you really need to be a blockbuster success. Otherwise, you are probably losing money. Indie game developers with smaller teams, they can afford to do this, but not all of them want to make 2D games or highly stylized, simplified graphics. User generation content is a good way of trying to generate more content from the player base, but it's not a fit for all games and not at the quality that a professional game team can create. What we're desperately in need for are tools that enable us to scale content production without scaling the human effort and the costs involved. Research, machine learning, and AI can be employed to create powerful tools to accelerate and scale content creation without the human effort, but while still retaining the ability for us to provide art direction to create the stylized worlds that are often common for video games. Microsoft Flight Simulator is an astounding example of content generation at scale, using machine learning, cloud computing, and photogrammetry. It's amazing how this data is seeded from real-world satellite imagery and weather data, along with contextual and ML and AI models to create a digital mirror of the world. The statistics in terms of the content generated at the level of quality achieved is astounding and simply unrealistic to create with human effort, especially when you consider that it is regenerated in 72 hours to reflect real-world differences. Now, if you think about this, how would we apply research to ground this and get the macro details as you walk around this world? What about all the interiors and the buildings and the prop placements? How would you make it a living world? Well, when we think of game virtual worlds, often it's not pure simulation, it's art-directed worlds, where we need artistic directed style transfer and really power tools to enable content creators to create their vision. We could create worlds that are created from game content to then seed new game environments that retain some of the unique gameplay properties and qualities necessary for that game. Really, we're talking about some of the tools that are going to be essential for creating the metaverse, for creating virtual worlds with a scope and details that evolve that are simply unrealistic to make with human effort alone. So let's talk about what some of these game content challenges are. We've already talked about virtual worlds when we looked at flight and the direction it could go. Game developers are more often creating large open worlds that are highly stylized. Some of the techniques that we would want to empower to enable art-directed creation are listed here. Things like terrain generation, prop placement, foliage, lighting, object modeling, texturing, material generation, and the ever-growing challenge of then optimizing that content so it's efficient to display while still being believable and realistic to the viewer as they play their game. Localization is a unique challenge that all games face. Really, one of the biggest issues here is that even today we are still manually sending our text and audio data to localization houses where humans, as mechanical Turks, if you will come back and localize the game with new text and new audio. Often we use cultural and local audio talent to create authentic voices. The cost of iterating on this is high, and we do it dozens of times throughout production. As a result, not all games are accessible to everyone in their locale. The challenge here is how can we evolve localization, text-to-speech generation to support more languages? But more importantly, how can we do it in a way that is perceived as native, not as clearly a synthetic or robotic voice? How can we match the cultural expectations beyond just a literal translation from one to the other? Can we retroactively translate a game without actually modifying it? An example extended into real time is in multiplayer games where we have players talking to each other, dynamically converting so they hear the players they're playing with in their own locale and the others are hearing it in the language that they understand. Character animation, another high-cost area of content creation, especially for AAA games, where we're trying to create believable character motion. Game teams today employ up to 50 animators, sometimes over 100 animators, classically trained animators, to be able to create the quality and scope of animation required. Game teams, because of this, limit the amount of variation and diversity in their animation in their games due to production costs. Stylistic variation, like different acting and different mood contexts. Diversity, like having female characters that actually move like female characters and not as reusing a large male animation set. Different ages, different heights, all of these play into the costs involved in creating the animation. When you're dealing with non-human animations, it gets even more complex. Motion capturing quadrupeds and animals is incredibly challenging, and often we need art-directed animation if we're creating something that you can't put in a motion capture suit. This video shows some examples of male and female walk cycles and how they change when they're, in this case, holding a rifle, and how the weight of that changes their motion and the way that they move. What we end up with is a combinatorial explosion. In this simple example, where you just have different walk, run, sprint cycles, different equipment you might be carrying, different stances, different genders, different energies, and different moods, the combinational explosion of the number of animations that need to get created quickly adds up and becomes cost prohibitive to create, motion capture, but more often to manually create, especially when you're dealing with stylistic animation. The challenge here is, how do we cost effectively generate complete motion sets with new styles and new variations? You can extend this to non-human characters. Non-human animation production would be a significant win. It's difficult to create this animation and very expensive. Could we create tooling and processes to enable animators to retarget, repurpose, and adjust animation onto creatures? Could you capture just a subset of animation and then extrapolate it to a larger animation set once you've understood and trained against those style differences? In this slide, you can see from Gears of War some examples of some creatures that are quadrupeds and their different animation sets all going through their walk cycles. And you can imagine these are not things that are easily created through without human involvement and human animators. So here are a few other bonus areas for player engagement challenges in the gaming space where research can apply and solve some very difficult problems. I'll talk briefly automation testing. The scale of bug detection and bug prediction and testing these large games requires large amounts of testers, large amounts of time and effort, and often affects the quality of the game if we're not able to capture and address these issues before a game is released into the wild. Detecting game-breaking design and content changes and predicting issues can really help accelerate and reduce that effort. In game development, it's really important for us to understand our players, their engagement, their preferences, their sentiment, understanding game economies and tuning them, skills assessment and prediction. All of this can be driven through data-informed prediction, machine learning, and research. Cheating is a big problem, especially in online games. Being able to detect anomalies, understand when someone is breaking the game by undermining the fairness of the economy, it can affect the sentiment and the longevity of your game. So I've talked a little bit about how we've seen exponential growth in content with game development and how that trend continues as we scale content to create ever more detailed and immersive worlds. Where the challenges and the opportunity is really applying modern research, modern machine learning techniques to this space. Ultimately, what we really need are tools that allow us to scale content production without scaling the human effort and costs to create this content. We've seen both simulated digital mirrors, which are critical for creating the metaverse and creating things like Microsoft Flight Simulator. But we also need art-directed tools that allow artists and content creators to feel empowered to have their vision expanded and multiplied through the power of modern machine learning. So this concludes my talk, and thank you very much.